Magnetic resonance imaging. How does an MRI work? So no doubt you're familiar with MRI or magnetic resonance imaging in some capacity, and perhaps even had one yourself. Simply put, an MRI scanner is a giant magnet that can produce pictures of the inside of the body. How in the world does it do this? And why is it different from an X-ray or a CT scan or PET scan or ultrasound, etc.? Could you even tell that this is a photo of an MRI and not a CT scanner? How can you tell? Why would a doctor order an MRI instead of some other type of scan? Is it better? If you've had an MRI, you're probably wondering why it's so loud, and why do they take so long, and why are they so expensive compared to other modalities? So this little presentation will be the first of several explaining how exactly an MRI works. And it is a complicated technology which, at its heart, is taking advantage of a quantum mechanical property of atomic nuclei to produce images. But truly, anyone can understand the basic physics of MRI, and this video will hopefully give the viewer some intuition for how magnets and nuclei can be used to produce images. In the first 2 minutes here, I'll give you the 30,000-foot view, and then we'll dive into the physics. So, first things first, MRI is based on the phenomenon of nuclear magnetic resonance, or NMR, and this will be the main subject of the first lecture. So, in short, certain atomic nuclei demonstrate the ability to absorb and re-emit radio frequency energy when placed in a magnetic field. This is the nuclear magnetic resonance phenomenon. Okay, so there's a lot to look at in that definition. Why certain atomic nuclei? Which ones get to participate in NMR? Which radio frequencies are we talking here? Kilohertz? Megahertz? And why a magnetic field? What role does the magnetic field play in making NMR work? And how strong of a field do we need? Well, here's a brief overview of the nuclear magnetic resonance experiment which forms the basis of MRI operation. So, first, certain atomic nuclei tend to behave like tiny bar magnets. We'll see why in a bit. But this means that in a magnetic field, the nuclei will align with the field just like a compass needle likes to align with the Earth's magnetic field. So that's step one. What an MRI does then is sends in a radio frequency pulse into the body to knock the nuclei out of alignment with the field. And this is where the NMR phenomenon kicks in. The nucleus will precess about the magnetic field, giving off its own radio frequency signal in the process. This is what the scanner detects. But it doesn't last forever. After a certain amount of time, the RF signal from the nuclei dies away. And the amount of time it takes for the signal to die off is different for different tissues within the body. It is called T2, and thus the process is called T2 relaxation. This is one method of providing tissue contrast in images. Finally, the nuclei will eventually realign with the magnetic field, and the amount of time it takes to do this is also different among tissues and is called T1 relaxation. So this process of knocking spins over, detecting their emitted signals, and waiting for them to realign is repeated over and over and over until enough signal is detected to produce a diagnostically useful image. Now, the key to understanding the NMR phenomenon, and thus MRI, rests in one very simple equation called the Larmor equation. Omega, the frequency of spin precession, is equal to gamma, a constant inherent to the specific nucleus we're investigating, times B, the strength of the magnetic field. The precession frequency, omega, is proportional to the magnetic field strength, B. If you double the magnetic field strength, you double the precession frequency, and thus the NMR radio frequency. And that is the tie between magnetic field and radio frequency. So with this overview out of the way, we can dive a bit deeper into each of these steps. But first, let's take a quick look at what is inside the MRI, as this will help guide our discussion a little bit. So if we look inside the scanner, we'll see three major components nested inside of each other. The outermost layer, which I'm coloring purple here, is the magnet itself, a giant, often superconducting magnet, which produces a very homogeneous magnetic field, or B0 field as we call it. It's about 10,000 to 100,000 times the strength of the Earth's magnetic field. So 90% of all that's inside the MRI is this magnet alone. And importantly, the magnet is always on. Weekends, holidays, whatever. From the moment the scanner is commissioned by the hospital, it is brought up to its operating magnetic field, or ramped, as they'd say, and ideally, it stays that way for its entire run. If you forget this important detail and walk into the scanner room without checking items on your person, your credit cards will be wiped, your wristwatch will stop, or worse, your pacemaker could stop, and any item with iron or ferromagnetic properties will be forcefully sucked into the magnet. And this is the most important safety concern with MRI. And as such, hospital staff are highly trained in proper patient screening and are carefully monitoring who goes into the magnet room. So the second layer within the scanner is the gradient coils, or gradients for short. While the main B0 magnet provides a strong homogeneous field, the gradient coils alter the B field in 3 dimensions by producing smaller magnetic fields in X, Y, and Z. This is used primarily to localize the RF signal in space. That is, the gradient coils are what allow us to know exactly where the RF signals are coming from within the bore, and thus produce 3D images of tissue. But they're also used to provide different contrasts, such as in diffusion or flow imaging. And I've drawn the gradient coils here as just a big green cylinder to show where they are on the magnet, but here's a more accurate image of what they look like. They're just coils of wire which produce linearly varying magnetic fields when current flows through them. And they're also responsible for the loud knocking and buzzing sounds the MRI scanner makes. Finally, the innermost layer contains the RF coils, which serve the purpose of sending the RF tipping pulse into the tissue and subsequently detecting the signal echoes from that tissue. The gradients in RF coils operate in a precisely timed concert to excite the nuclei in a specific location within the body and detect the resultant signal echoes. That is, the RF coils are just radio antennas designed to deliver a very homogeneous radio signal to tissue. As a quick aside, MR folks will often refer to the gradient coils simply as gradients and the RF coils simply as coils. We'll dive deeper into coil design and operation later, but for now you just need to know these 3 components and the fact that the main magnet creates a large static and homogeneous field on order of a few Tesla. The gradients vary the magnetic field in space on order of millitesla for spin localization, and the RF coils create time-varying magnetic fields on order of tens of microtesla for the purpose of exciting spins and detecting their echoes. By the way, the fact that we're just using radio frequency here means that MRI is completely ionizing radiation free. It is completely safe and can be used serially and in pediatric patients with no concerns whatsoever. Okay, now let's dive into the physics. How does the MRI actually work? So in a nutshell, right, like we've said, an MRI uses a very, very strong magnetic field to create a very, very slight magnetization in the nuclei of atoms within the body. Now, there's lots of different elements in the body we could look at, but in terms of number of atoms, by far the most abundant is hydrogen, the nucleus of which is just a single proton. All clinical MRI look exclusively at hydrogen nuclei because of its abundance, its high gyromagnetic ratio, we'll get into that in a bit, and its presence in nearly every organ within the body. So there is, after all, 2 hydrogens to every water molecule, and the body is about 70% water. So let's zoom in on a single hydrogen nucleus and see what's going on. Here is a lone proton, or hydrogen nucleus. Of course, there are protons in all atomic nuclei, but in MRI world, we often say proton imaging, even though it's only the lone protons of hydrogen nuclei we're looking at. Yeah, a bit of a misnomer, but what can you do? Yeah, so unless otherwise specified, when I say proton, I'm specifically referring to the hydrogen nucleus. Anyways, so the proton has several properties that we can look at. We're all very familiar with the concept of mass. We're also familiar with the concept of electric charge, but we're perhaps less familiar with another equally important property called spin. And spin is the property which we'll be leveraging in MRI. Now, spin is an entirely quantum mechanical property of particles, which is largely why it's less familiar to us. But that doesn't mean we can't develop an intuition for how it makes particles behave. Spin essentially gives our proton friend 2 important properties. First, as its name implies, spin is a measure of intrinsic angular momentum. And this means that our proton behaves as if it's actually spinning. And I very deliberately say as if it's spinning, when I really just mean that it obeys the canonical commutative or angular momentum. But for now, the spinning model is fine. The second property we get from the spin is the proton's intrinsic magnetic moment. That is, it allows our proton to behave like a tiny, tiny bar magnet. So the magnetic moment is described in terms of the particle's spin quantum number, and also a constant called the gyromagnetic ratio, represented by gamma, highlighted purple here. The gyromagnetic ratio is an empirical constant specific to whatever nucleus we're looking at, which describes essentially how big its magnetic moment is given its spin. And he'll be important to us in a bit, but for now let's just focus on what happens when our spin is placed in a magnetic field. So, the presence of a magnetic field, often represented by B, shown here with the pink arrow, will affect our spin. First, our magnetic moment will try to align with the magnetic field, just like a compass needle tries to align with the Earth's magnetic field. But what happens when you try to change the direction of a spinning object? We're actually all pretty familiar with this phenomenon, as this is exactly what happens to a spinning top. Gravity tries to get it to fall over, but because it's spinning, it actually exhibits a different motion, which we call precession, about the force of gravity. This is exactly what happens to our proton. The field tries to torque it in line, but because it has angular momentum, it instead precesses about the magnetic field. And this is the NMR phenomenon. Now, imagine that I were to place a coil of wire next to our proton. We'll call this our NMR coil, or RF coil. Because our proton behaves as a bar magnet, a magnetic field is now sweeping across the coil, and the magnetic flux through the coil is changing. Magnetic flux is often represented by the Greek letter phi, and you can see that it is changing sinusoidally in time with a specific frequency, omega, which is just the precession frequency of our proton. Hopefully you remember from physics class that a changing magnetic field near a wire will induce a voltage in the wire. This is called Lenz's law. Changing magnetic flux yields a voltage difference. And this is how we detect the NMR of a proton. The changing magnetic flux through the coil induces a signal, which we then detect. Okay, so what does the signal look like? If you were to plug your coil into an oscilloscope, what would you see? Okay, so again, it will follow the familiar sinusoidal pattern, or cosinusoidal, and now we get one of the most fundamental concepts in NMR summed up in a simple equation called the Larmor equation. Omega equals gamma times B. Omega, the precession frequency of the proton, is equal to its gyromagnetic ratio constant times the magnetic field strength. This equation says, first, that nuclei with different gyromagnetic ratios will precess at different frequencies in the same magnetic field. Also, if we increase the magnetic field strength, the nucleus will precess faster and will detect a higher frequency signal. And this relationship is linear. Now, notice how I've animated this plot here. Not only does the frequency increase when we increase the magnetic field, but so does the amplitude. In fact, the amplitude scales with the magnetic field strength. So remember Lenz's law. It's the rate of change of flux that produces the voltage. And as the flux changes more rapidly, i.e. the precession frequency increases, so does the voltage amplitude. For those that are remembering their calculus right now, this implies that a factor of omega is pulled out front of our signal equation, and since omega equals gamma b, we can substitute those and see that increasing the magnetic field will increase our signal amplitude. And this is a common practice in NMR and MRI. We're always trying to go to higher field strengths to get more signal, although it's always expensive when you do that. Okay, but there's more here. Notice the angle our spin makes with respect to the magnetic field. If that angle is increased, the magnetic flux through the coil will increase. And likewise, if this angle is decreased, the flux decreases. So we call this angle the flip angle of our spin, and we'll see why it's called that in a bit. But in a nutshell, the more perpendicular to the field, the higher the signal. This effectively places a sine of theta in front of our signal equation as well. Now, the physicists in the audience might be dubious at this point, saying, flip angle, huh? But I thought that a spin 1/2, as it's described in quantum mechanics, can only be in one of two states, either spin up or spin down, no in-betweens. This is correct. A magnetic field can only have spins occupy discrete energy states, but what our precession model is actually describing are quantum mechanical transitions between these two states. And this is a bit beyond the scope of the presentation, but rest assured that the concept of flip angle is accurate even quantum mechanically. Also, discrete spin states will show up later in the presentation when we talk about spin polarization, so get excited for that. Okay, so finally, all of this discussion has been focused on the behavior of one spin so far, but in fact, we're detecting NMR from billions and billions and billions of spins, all precessing about the magnetic field. The more spins you have to look at, the greater their collective magnetic field and the higher the signal. So we have one more factor to add in here, which is N, the number of spins contributing or participating in the NMR signal. So we see here that the intensity of our detected signal depends on a few things: the number of particles we have, the sign of the flip angle, our particles' gyromagnetic ratio, and the magnetic field strength. So I want to discuss the dynamics of this signal next. So for now, I just want to combine all of these parameters into a single variable A, which is just our signal amplitude. So to discuss the dynamics of signal, I'm going to change the camera around a little bit here and take a top-down view of our spins. So in this orientation, the magnetic field is coming out of the screen. Now, you may have guessed that the key to all of these spins giving a detectable signal relies on the fact that they're all perfectly in sync or coherent with each other, all pointing in the same direction at all times. Only in this way can the vector sum of their individual magnetic moments add up to a magnetic moment big enough to detect. Well, as it turns out, the perfect coherence of the spins doesn't last forever. The randomly distributed spins experience the external magnetic field and also the magnetic fields created by each of their neighbors. So some spins are precessing ever so slightly faster and some ever so slightly slower. And the result is that over time the spins become dephased and the NMR signal is lost. So knowing that, what would you expect the detected signal to look like? And in fact, it looks like this: a decaying exponential. Mathematically, this would be expressed like this, where our sinusoidal behavior is now multiplied by e to the minus t over t2. The t2 here expresses how quickly the signal decays. And this particular plot is called the free induction decay, the signal you detect when immediately after exciting your spins. We see this enough that it gets its own name, and we should take a closer look at it. So I'm going to highlight the decay time t2 with a green line here. If the spins dephase very quickly, our signal decays quickly, and t2 is short. Tissues with a short t2 would include bone and lungs. Their spins do not stay in phase for very long. Likewise, a long t2 would indicate that the spins retain their coherence for a much longer amount of time, and their FID decays slowly. This would include more fluid-like tissues such as water and blood. And of course, all different tissues within the body exhibit the whole range of T2 values. And this is the key to contrasting tissue. So for an example, here's an FID of tissue with a short T2, indicated by the T2S for short. And here's the signal from a tissue with a medium-length T2 and a signal with a long T2. How can you tell these tissues apart in an image? Well, first, I think these plots are a bit messy as they appear here, so I'd like to get rid of the wiggly sinusoid pattern if I can. After all, I'm only interested right now in their decay rates, since they all have the same omega. This is actually a simple mathematical trick. Just let omega in the cosine function equal 0. Cosine of 0 is just 1, so now we're only looking at the signal decays for each tissue. NMR physicists call this transitioning to the rotating frame. If omega is 0, that's the same as saying the spins aren't precessing, which is exactly what you'd see if your frame of reference was spinning at the same frequency as omega. And fun fact, there are times when not all tissue omegas are the same, such as between protons in water and protons in fat. And in this case, the frequencies would be a source of contrast, and it'd be helpful to keep them, but we'll dive into frequency shifts in a later lecture. Okay, so getting back to our differently decaying signals, the key to differentiating these three signals in the NMR experiment comes down to how long you wait to detect the signal once the spins have been knocked out of alignment with the field, or excited. We call this the echo time, or TE for time of echo. This is a parameter chosen by the MRI technician deliberately to maximize contrast between tissues, which the radiologist is interested in differentiating. So check this out. For the echo time I've drawn in our cartoon here, each tissue would deliver a different signal strength. And this corresponds to the different brightness of tissues within the MR image. Green, which still has plenty of signal, would appear bright on our image. Red would appear gray, and blue, whose spins got out of phase with each other very quickly, would appear black. This method of producing tissue contrast based on signal decays of differing tissue is called T2 weighting, since T2 is the parameter which effectively determines the contrast. Now, you may be tempted to call each point in the image a pixel, short for picture element, but they are in fact voxels, or volume elements, the 3D analog of pixels. This is because the image represents a slice of the body which was acquired with a definitive thickness, although imaging people may use pixel and voxel interchangeably. So anyways, you now have an idea of what a T2 weighted image actually is. Every voxel effectively tells you how quickly the processing spins in that voxel got out of phase with each other. Bright if they dephase slowly, dark if they dephase quickly, and because T2 is characteristic of its tissue, the resultant image presents an anatomic map of tissue. Cool, no? So, now those of you who are keeping the math in the back of your mind know there's more to examine here. So I'll simplify the discussion with only two tissues here, red with a long T2 and green with a short T2. Like I said, selection of the scanner's echo time is what determines the contrast, but it's not the only thing. Notice in this plot that both the red and green, though they have obviously different T2s, have the exact same amplitude at T equals 0. But this is not always the case. So what determines this amplitude? Well, remember when we combined all of our amplitude parameters into A? It's time to bring those back. So a question for the audience, which of these parameters would likely be the most different between tissue? So generally, the whole tissue experiences the same magnetic field strength. They're all protons, of course, and thus have the same gyromagnetic ratio. We deliver the same flip angle to the whole sample. But not all tissue molecules contain the same number of protons, again, hydrogen atoms. This means that the amplitudes for our red and green tissues here may also be different due to differing numbers of protons, and we can now include this more explicitly in our decay equations. And note now that our decay plots may be scaled differently. Here you can see that even though green is more protons and thus starts out with a higher amplitude because it decays more quickly, red would give off more signal at later times in the FID. Notice in particular that there is a point at which both tissues would give off the same amplitude and thus could not be differentiated if we were to choose our echo time here. So, in fact, in this sample, it seems the quicker we can detect the signal, the better. An echo time of 0 would provide maximum contrast. If we choose our echo time to be 0 in this example, the exponent goes to 1, and we're left with just the number densities. If you were to acquire your MR image with these parameters, you would get what we call a spin density image, since now the different brightness between tissue would reflect the differing numbers of protons that they each contain. No weighting due to spin dephasing is contained in this image. And notice that there isn't a whole lot of contrast between tissues here. Spin density images aren't the most useful in the brain since most all neuromatter has similar proton densities. So spin density imaging is more common in other organs. Okay, so there's one more source of contrast we need to consider before moving on, and that's T1 contrast. So as soon as the spins are tipped out of alignment with the magnetic field, they start the process of realignment. This process is slower than the rate at which they dephase due to T2, so you notice here that I began the realignment animation with the spins already completely dephased. But watch as their magnetic moments slowly realign with the magnetic field pointing upward. what would the vector sum of all the spin's magnetic moments look like in time here? Well, I'll plot it. Initially, all the spins are perpendicular to the field and thus exhibit no longitudinal magnetism, but in time, the magnetism slowly grows toward the purple line, which represents the magnetization the sample has when all spins are realigned with the field. Notice the peculiar shape of the realignment curve shown in cyan here. Looks a bit like the voltage across a charging capacitor. In fact, the magnetization follows the exact same math as a charging capacitor shown here. The purple M0 is the magnetization represented by the horizontal purple line and is called the sample's Boltzmann magnetization. And the rate at which our magnetization recovers to this value is given by T1, highlighted yellow in the equation. This is another source of contrast in MRI. Similar to our T2 discussion, different tissues exhibit different T1s, which can be used to differentiate tissue. This is called T1 weighting. And again, the scanner operator chooses the specific time at which the signal is to be measured. In the context of T1 imaging, this timing parameter is called the repetition time, or TR, time of repetition. So whereas TE is the amount of time the scanner waits following spin excitation to detect the signal, TR is the amount of time the scanner waits in between excitations. If the TR is on order of tissue T1, then for tissues with long T1, the spins won't have realigned as much with the field and their longitudinal magnetization will be low. Thus, the image brightness will be low. Likewise, tissues which realign with the field quickly will have more magnetization to be detected on excitation and will thus appear bright on a T1 weighted image. Just to reiterate what we've been talking about, T1 and T2 are intrinsic properties for the tissues, whereas TR and TE are parameters chosen by the MR tech and how the scan will detect the T1 and T2. So just important to keep those straight. So this is how we conduct the NMR experiment. We knock spins over, detect their signal as they dephase, wait for them to realign with the field, and then knock them all over again. After many of these NMR experiments, each one in the presence of a different magnetic field gradient scheme, we'll talk about that later, we can acquire enough signal to produce an image. And here's an animation of the total magnetization vector of all the millions of spins in our sample. Note that we can decompose the total magnetization vector into two components. The longitudinal component, which grows at a rate T1 following excitation, and the transverse component, which decays at a rate T2 following excitation. Further, we note that the transverse component is the magnetization which is actively delivering detectable signal to the scanner by Lenz's law, and the longitudinal component represents the magnetization which we currently have available for the next excitation. Now you might notice that the total magnetization vector follows a corkscrew path to realignment. This is actually a bit of a pain to deal with mathematically. In fact, our discussion of the dynamics of these vectors can be made much simpler if we choose a coordinate system, which isn't stationary relative to the motion of precession, but rather rotates with the precessional motion. Earlier I alluded to a rotating reference frame. That's what I'm showing here. We construct a frame of reference which rotates at the precession frequency of our nuclei. In this reference frame, the relative motions of our vectors are much easier to describe mathematically. You simply have to recognize that any part of the magnetization vector in the transverse plane will produce detectable signal, and that longitudinal part of the magnetization vector is always growing toward equilibrium at a rate T1. So, for instance, the process of excitation is much easier in the rotating frame. The way we tip our spins into the transverse plane is by sending a radio frequency pulse, which we call B1, perpendicular to the main magnetic field B0, and of the same Larmor frequency omega as the precessing spins. So why does this work? Well, notice that in the rotating frame, if the frequency of our B1 field matches the precession frequency, and therefore the rotation frequency of our frame of reference, then it will appear stationary in the rotating frame. Our spin will therefore precess about this magnetic field. So once it is at the flip angle that we desire, we turn off the B1 field and detect the resultant NMR. See how this looks in the laboratory frame of reference. And notice here that just like in the rotating frame picture, both the moment and the B1 field rotate at the same frequency, and therefore B1 is always perpendicular to the spin. The difference is that the mathematics describing this behavior is much more complicated in the lab frame than in the rotating frame. Now a 90-degree flip will take all of our longitudinal magnetization and convert it entirely into transverse magnetization. Thus, the signal observed as a function of time after our spin flip is proportional to the longitudinal magnetization times our T2 decay. But notice the role that the repetition time TR plays here. Remember, it is the amount of time in between successive spin flips. If our TR is short, then very little of our longitudinal signal will have been recovered, and as a result, our excited transverse magnetization is smaller. If we wait a bit longer, we'll have more longitudinal signal to excite, and we'll detect greater signal. Longer still, if we make TR even a bit longer, you get the idea. So, note that while longer TRs do indeed result in higher signal, it will also result in a longer scan. T1 is a much longer process than T2, and as such, TR, by definition, is longer than TE. So if you increase TR and do it lots of times, you are guaranteed to increase your scan time. So the compromise between scan time and signal fidelity, well, is a topic we'll get into later, but that is the sort of game that your MR technician is trying to play when developing a sequence.